All right, I'll just go ahead and get started with this class. The roll sheet is being passed, so make sure you sign the roll sheet because I suspect some people may not remember to do that sometimes. All right. Well, let's start with a new homework assignment, because that usually gets the attention. New homework assignment called Mixed Up. So this one is kind of fun. Okay, so the format of the homework assignment is about the same as the last one. You can see that I borrowed a lot of text from the previous assignments. Just the file name is now changed, the folder name is changed, and the file name has changed. Otherwise, it's basically the same thing. You download a tar.gz file, you upload it to the virtual machine, you untar it, and then you work on the homework, you retar it, you submit it, and that's that's the procedure. Yep.
So if we just return in the last assignment, would you have credit?
You don't have
to answer that. Don't worry.
I'm thinking of the best way to answer it, and still be okay on to be recorded. So that's the difficult part.
How about we get half credit on the part that's changed?
Yeah, the part that's changed. Let's take a look at this file, okay? Because this is a good good way to get started with the class because now you guys know what the homework assignment is about. So when we talk about those concepts, hopefully it will start to click a little bit more quickly. So let me go ahead and open this up. And this is the file. We'll go ahead and just open it up with my trusty VIM. And pick a bigger font. There we go. Is it big enough?
Yes.
Yes? Okay. Okay, the program objective, pretty easy. At checkpoint 1, register EDX should have a value of hexadecimal 40002323. Okay? In other words, it's just a bit pattern that has to be there. You are only allowed to replace the question marks with values. That's the only thing that you can do. You cannot add instructions. You cannot remove instructions. You cannot change the labels. You cannot add additional labels, and so on and so forth. So you guys know the restrictions already. Alex, that's not just water, is it?
It has a lid.
Uh-huh. Okay, let's try not to do that, okay? Because I don't want any sugary residue left on the floor, just in case. Okay. So here's the program. The program starts with the usual stuff, a bunch of data definitions. And by the way, the .data, .int, these are called directives. Or because they're not instructions. They're not instructions that you can actually execute at runtime. These are instructions only to the assembler. They're not actual instructions that will execute at runtime. So they're called directives. Okay, anyway, we have 3 label definitions. The first label is L1. It is defined to be the value of another label called L2. L2 is a label, but the 4 bytes at L2 is also defined to be the value of yet another label, which is L3. So L3 is over here. Okay? So, right, yes, go ahead.
Is it okay that we're because we declare them later, so
it is okay. It will resolve it. As long as they're in the same file, they will get resolved. Forward reference is fine. There's no problem with forward referencing in assembly language programming. In C, you cannot do it, but in assembly programming, it's fine. This will assemble. And here we have,
Even if we leave the question marks in?
No, not with the question marks. So the question marks, are there's one here, and there is one here. Those are the 3 question marks. I do not know whether the solution is unique or not, which is good. If it is not unique, that means, if you can get it to work with other, values or values other than the one that I think, will work, that's fine. As long as by the time we get to checkpoint 1, before I execute this instruction, I need this value to be in register EDX, not EAX, EDX this time. You cannot change the instructions. In other words, this instruction has to stay put. This instruction has to stay put. All instructions have to stay put. The only thing you can do is to change the question mark to certain values. Okay? So what we need to know is, well, the first thing that we need to know, which is something that we have already talked about, is the indirect addressing mode. We talked about that on Tuesday, so that's already done. The second one that you need to know is called the based addressing mode. This is called the based addressing mode. It looks almost exactly like an indirect operand. It's just called based because it is a very slight change. It's a very slight modification on top of an indirect operand. This one here, there's nothing you have to do about it. This one has to be the way it is. There's no question mark. You cannot change it. And the last one is this one here. This is called the based scaled indexed addressing mode. Okay, which is quote unquote the most complicated one of them all. Okay, so that's your homework assignment. So I'll keep this open, and then when we talk about the concepts, we'll hopefully be able to associate what we will talk about today with the homework assignment. So we are in topic 2 right now, and there was a few questions. There were a few people asking when are we going to have our first exam, and the answer is we don't have enough material yet to have our first exam. So we'll probably have a practice exam sometime next week, which means the actual exam is going to be 1 week after that. So we are running a little bit behind here. And we are currently still with addressing mode and memory allocation. So we'll go ahead and take a look at this one. So here's another digression, CISC versus RISC. We'll come back to this digression later, okay? Because I want to talk about the addressing modes, and then we'll come back and talk about, what is CISC and what is RISC, and why is it worthwhile to have RISC processors. So we'll skip all the way to 5.8 and talk about what is the based addressing mode. The based addressing mode is basically an indirect addressing mode, but on top of an indirect addressing mode, you can add what we call a base. Okay, this 2 here is called a base. Now, what happens without the 2 here as an indirect operand? What do you think this instruction will do without the 2 here? It will copy a byte with the 0 pattern to the byte location at EAX. In other words, we look at the current content of EAX as an address, and then we say, okay, we'll just go ahead and overwrite that location with a byte of 0. Is that okay so far? That's the indirect addressing mode. This is easy. This is saying, instead of going to that location, that exact location, and put a 0 there, we'll go and put a 0 at 2 bytes after that specified location. This 2 is added to the value of EAX. The sum of these 2 become what we call the effective address, the actual address of the bytes that will be changed. Is that okay? Just normal summation. You add this number, whatever it is, to the value of the register at the time when this instruction executes. The sum of the 2 become the address, and the byte or bytes at that location will be modified in this case because they are the destination of this move instruction. Yep.
So let's say EAX pointed to label 1. If we wanted to do label 1 plus 2 is what that's representing?
That is correct. That is absolutely correct. Very good.
Can we do subtraction with that?
You can do subtraction. You can specify a negative number. Yep, definitely. So there are many ways to do it. You can also have L1 here and have a negative 1 put into EAX. That will accomplish the same thing. Do you see what I mean? Because it's just adding the 2. It doesn't matter which one is L1. You can have L1 instead of 2, and then EAX has having a value of negative 1. Or you can do it the other way around and put a negative 1 on the outside and initialize EAX to be L1. So either way works. Okay. And do you guys still remember what we talked about on Tuesday? Never trust tag, right? So how do I write a simple program to double check and make sure that this is exactly what a based addressing mode will do?
Check the value of the register after it's made.
Exactly. So we'll go ahead and write a simple program to do exactly that. And let's see, should I start a new? Yeah, I'll just start a new shell. And minimize the other one. Has anyone downloaded the code that I wrote on Tuesday? You know, the whole zip file? No? Okay, was it useful?
Yeah. Actually, I just rewrote it and just put it as example mem1, and then it's very helpful.
Okay, that's good. I'm glad that it was helpful. So I do this a lot in my classes. You know, I just use sample programs on the fly to illustrate the concepts. So it is particularly important in my classes to have a possession of those files, or at least know what kind of sample programs I used in the class. So we'll go ahead and start with I'll just call this based because it is the based addressing mode. Dot data. And just to make this a little bit easier, I will have L1, and I will use dot fill to fill up a certain region of memory with a particular pattern. I will fill up, let's say, 4 spaces, okay, 4 things. Each thing is 1 byte, and each byte has a value of, okay, it doesn't matter which one, A5, okay. So this will give me 4 bytes. It will allocate exactly 4 bytes, and those 4 bytes will be initialized to the hexadecimal value of A5 before the program starts to execute. Any questions? I could have done the same thing with a .int 0x A5 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 A5. That would have done exactly the same thing. And then we switch back to the text section. .global to export the label called _start, and then I define the _start label to be here. So the first thing I would do is to illustrate the first point. In other words, I will initialize EAX to be L1. In other words, I use EAX as a pointer. And then I will go ahead and move a byte. As long as it is not A5, I will prove my point. So I'll just move a 0 to the location of, let's say, 2 bytes after wherever EAX points to. Is that okay?
The third byte should be 0.
That is correct. The third byte, should go from A5 to 0. Okay. And then I will go ahead and change another byte, using the next instruction. So the next instruction, in the next instruction, I move, let's say, 1 into EAX. I reuse EAX, in this other instruction. And this time I'll move. Let's not move 0 again, because otherwise we cannot. It's not as easy to differentiate. So this time we'll move another byte number. Let's say 20. Okay, we'll move 20 in hexadecimal into L1 open parent EAX. Okay, but remember, we're just adding the 2 numbers. We're just adding the whatever is outside of the parentheses to the value of the register inside the parentheses, and then we get to the address. So this time it is basically EAX plus 1, or L1 plus 1 will get a value of hexadecimal 20. And we'll just call this, the entire program. Since I may not actually finish running the entire program, it is not really that important to finish up the program with this exit sequence, but I'll just do it anyway, so that the program is complete. Yes, sir?
Can you go over move the last part of it, like move B?
This one here?
Yeah. Can you go over that again?
Sure. Okay, the instruction is move, MOV, which means copy. The width, or the number of bytes I'm copying, is just 1, because B stands for byte. The first operand is an immediate operand because it starts with a dollar symbol, and the actual pattern, or the actual value I'm moving or copying, is 20 in hexadecimal, because 0x is the prefix of a hexadecimal number. The destination is this operand here. This is a based operand just like the other one. So I would basically add whatever the value of L1 is to EAX. The sum of those two will become the effective address of whatever byte I'm going to change. Yep.
If you have compounded bases, I guess, like if you were to do L1, parent 1, parent EAX.
Nope,
Like
nope. You can only do it like this. This is the format of the based addressing mode. Okay. So are we doing okay so far with the syntax and also the meaning of the instructions? So after this entire program, the 4 bytes of A5 should, 2 of those should be changed. The second one should become 20, and the third one should become a 0. The first and the last should remain as A5. Is that your expectations? Okay. Let's go ahead and run the program and see if that's exactly what it will do. Base.o, base.s, LD, and then we run the debugger. Go ahead and put a breakpoint. I forgot something that's important. That's okay. I can always put a breakpoint on line 8 instead of line 7. Okay. The only value of putting a breakpoint on line 7 is to look at the value of EAX. But since we are not really interested in the value of EAX before the first instruction, it's just as good to put a breakpoint on the second instruction. So we run the program. Okay, so at this point, I have not changed anything in memory because this instruction has not executed yet. In other words, the only thing I have done so far is to initialize EAX to a specific value. I have not yet changed any memory locations. So this is a good time to use the X command to take a look at the location L1 and make sure that we do have 4 A5 hexadecimal values at those locations. It's the X command, and we want to display 4 things. Each thing is a byte, and we want to display each thing as a hexadecimal number. So that's why we have the command x/4bx.
Wouldn't it be 4xb?
Huh?
Wouldn't it be 4xb?
4xb would work just the same. Actually, both will work. You can change the order.
Oh, okay.
They do not share the same letters, so you can mix and match.
Oh, okay.
The instruction seems to suggest that it has to be the format first and then the width, but you can actually flip it around, it will still work.
Oh, okay.
And we want to use the address of L1. Remember, the GDB misunderstands that L1 is an integer. So we have to, but since L1 is an integer, we are not interested to use the integer itself as the address. We're interested in the address of the integer. Okay. And sure enough, we have the 4 A5s at the label L1, and this is the value of L1. In other words, the label L1 at this point has a value of 8049098 in hexadecimal. How can we check that? Oh, that reminds me, I just moved that value into EAX. In other words, if I do an IR EAX at this point, EAX should have exactly that value. Let's double check. IR EAX. This is the decimal representation. We're not that interested in the decimal representation. This is the hexadecimal representation, and you can see it is exactly the other one. It is an address. Are we doing okay so far? So now we are ready to execute the second instruction. The second instruction will in fact change one of these 4 bytes to 0.
You just step.
I can use single step. Yeah, I'm just using single step to step through it. So every time I press enter, it will only execute 1 instruction. Now is a good time to take a look at those 4 bytes again, and sure enough, the third one is changed to 00. Now remember, we count from 0 in programming. In other words, this byte is L1 plus 0, L1 plus 1, L1 plus 2, and that makes sense. Okay? And this is why when you have indexing in C, it is 0 oriented. Because the first item is the first item of the entire array, and that's why you can specify an index of 0 to refer to it. Okay, so this one is already done. We are now on to the third instruction. This is our third instruction, moving 1 into EAX. Single step. Well, we can always double check, but this time there should not be anything surprising. EAX should have a value of exactly 1. This is our next instruction to execute. EAX has a value of 1, and this is just L1 itself. L1 plus 1 is going to be the destination. That's the address of the destination. That will be changed to 20 in hexadecimal. Okay, so we want to double check, make sure that our memory is not modified in any way up to this point, and you can see that only this location is modified, and my expectation is this byte will be changed to 20 in hexadecimal after the next instruction executes. Are we doing okay so far? So now we single step, and we take a look at the memory locations again, and this time the second byte is changed, which is L1 plus 1. Okay? So basically this program doesn't really do anything useful other than illustrating the concept of the based addressing mode. Yep.
So if you want to access the 0th location, you don't have to put any base number on it?
That is correct. Okay, based on this setup here, you can put a 0 here, but if you put a 0 here, it becomes exactly the same just as an indirect operand. Right? The indirect operand is like a base operand with a 0 as the base. In other words, there are several ways to express exactly the same thing, and that's a very common property of a CISC processor. There are many ways to do exactly the same thing. Are we ready to move on to the next one? Does everybody understand what the based addressing mode does? It's just adding the two. One is fixed, the other one is a register, which means the value changes at runtime, but you add those two and the sum becomes the effective address of the location that you're interested in. It can be a source, can be a destination, it is a memory operand. Are we doing okay so far with the concept? Okay. It is just one little step on top of an indirect operand. We can specify basically an offset to the location. Are we doing okay so far? Okay. So then we move ahead to the next one. The next one is not really that much more complicated. It's called a based indexed addressing mode. And the way it looks is like this. A based index operand is like a based operand, except it specifies one additional register called an index register. The sum of the displacement is whatever you specify outside or before the open parenthesis, the value of the base register, which is the first register that you specify in the parentheses, and the value of the index register, which is the second register that you specify inside the parentheses. The sum of these three items become the effective address. So it's just one extension on top of a based operand, because we just have one more register called an index register, and we add all three numbers up, the summation becomes the effective address. In this case, the source operand of this example is the value located at the effective address, that is the sum of two EBX and EDX. Because in this case, EBX is the base register, and EDX is the index register. Note that it is possible to specify no base register. In other words, you can leave the base register as nothing and specify a comma. That is actually allowed. In that case, the base register, the quote-unquote base register, which does not exist, supplies a value of 0.
Would that be the same thing as a base addressing mode?
Yes, it would be exactly the same thing. As I said, a CISC processor gives you a gazillion ways to do the same thing. Okay. Shall we test this kind of operand, or shall we move on to the next one? Yep.
Can you clarify again what in those two, inside parentheses you said the first one was the base and the second one was the index?
Correct. The first one is the base register, and second one is the index register.
I just wasn't sure of those terms.
It is important to know those terms, because the next one, will.
Get more
In this case, it does not matter with the order, because when you're adding numbers, it is commutative. But in the next slide, it becomes important. Yep.
The 2 at the beginning of that line is always bytes, or is it the same unit as the...
It is always bytes.
Okay.
You mean this number here?
Yep.
Yeah, that number is always in terms of byte locations, because the 386 processor is a byte addressable processor, so when you specify an offset, it is always specified in number of bytes. Okay. All right. Well, let's go ahead and just test this and see if we can double check and see if I'm wrong, because remember, do not trust me. Okay. So based index.s, and we can start with something that is just as easy. Okay, we'll say L1 dot fill. I don't know. This time we'll fill up 20 things, and each one is 1 byte, and each one is the bit pattern of I don't know. Let's say EC. Okay, and then we switch back to the text section. Same stuff here. And this time, just for illustration purposes, I'll just illustrate one example. You guys can pick this up and then change it to illustrate additional examples. I'll just put L1 into register EAX. I'll put, say, 5 into EDX. And the third instruction is the one that I want to use. So I'll move W in this case, just to have some variation. A pattern of 0 using 2 bytes, and the destination is going to be, let's do some math here. Okay, the base is -2, the base register is L1, but displacement is -2, and then the base register is EAX, and then the index register is EDX, like that. Okay, so are we doing okay? Which byte do you think will be overwritten by a value of 0?
The third byte?
The 4th byte, because 5 minus 2 is 3, but since we count from 0, so it is technically speaking the 4th byte that will be reset to 0, cleared to 0. Okay, are we doing okay so far? Okay, now that we know what to expect from this program, we can just go ahead and finish it up, and then we can run the program in GDB so that we can see the result of this program. Oops. There we go. And we put a breakpoint on line 8. Okay. It's really, we don't really need to do that. Line 9 is the only one that will change the memory locations, but we'll just put a breakpoint over there anyway. First thing is to make sure that we do have 20 ECs. Okay, so we say x/20 xb, and starting at the location L1, and you can see that we do have exactly 20 bytes that are all initialized to the value of EC. Okay. Any questions about this part? Okay. No questions. We can also double check what is in EAX itself. So IR EAX, you can see that EAX has this same bit pattern as L1 itself. Okay, so this is something that we already know. Now we single step so that EDX will have a value of 5. Double check. EDX does indeed have a value of 5. And then we execute the third instruction, which is the most interesting one, because we want to see what the based indexed addressing mode can do. So single step, and then we go back to the X command to take a look at the memory content, and you can see that this is our first, second, third, and this is our 4th byte. It is in fact reset to 0 because of the...
Fifth byte.
This is the 5th byte? No, it's the 4th.
The fifth byte is also.
Oh, the 5th byte is also because
Oh, we did it
of
W.
what?
You did it W.
Because we moved W. Yep.
What W is that?
Hmm?
What the W that?
Word.
Huh?
Word. It specifies a word, and the word is 16 bits, 2 bytes. Okay? Any questions about this code? No questions? Okay. Now we can also go back and change it just a little bit. Okay, we can go back and change it so that it does not have EAX. So instead of changing this instruction here, I'll go ahead and start with another instruction. So I would just put L1 over here, and this time I would not specify EAX. Okay, just like that. And this time, which byte do you think will be changed? Oh, that's also changed, moved. So this time, which byte will be overwritten by a value of 20 in hexadecimal?
The 5th byte?
The 6th byte. Okay, the 6th byte, because without the base register, we are just adding whatever is outside of the parentheses and the value of EDX at the time. EDX has a value of 5. We haven't changed that. So it's basically L1 plus 5, which is the 6th byte of the sequence. Okay, so we'll go ahead and retry the program.
What do you do with the exclamation point?
The exclamation point is, recall from history the last command that starts with AS.
Oh, that is so cool.
Yeah, try that in DOS. The shell, I probably use about 2% of what you can do in the shell, in Bash. You can do a lot more than just that. You can recall a command and probably do a search and replace pattern so that certain parts of the command is replaced. I haven't really got to that point yet. Because if I have to do something like that, I will just write a script to do it. Okay, so here we list the program, put a breakpoint. Let's just put a breakpoint on, okay, let's see. Let's put a breakpoint on line 11 because we already know what the previous part of the program is going to do. So we put a breakpoint on line exactly 11, and we run the program. We go back to the X command, x/20bx $L1. So we have the previous result of this program. The 4th byte and the 5th byte are both reset here. And we're expecting this byte, which is our 6th byte, to be changed to a 0x20. Are we doing okay so far? Okay. So as we single step the program, and we double check the memory locations, and sure enough, that byte is now changed to 20. Okay. Is there any surprising at this point? No. Is there anything exciting going on right now? No, because we all know how to add numbers, right? I mean, so it's not really that exciting. The next addressing mode is a little bit more exciting because now we can actually multiply. Wow. The next addressing mode is called based scaled indexed addressing mode. Okay. Yeah, I can imagine the file name is going to be BSI because I don't want to type, all the words. So this is similar to a based index operand, except a scale can also be specified. The scale is an integer that is either 1, 2, or 4. Cannot be any arbitrary integer, has to be 1, 2, or 4. The operand is the value at the effective address. Okay, so you should know what is an effective address at this point. But this time it is the sum of the displacement. The displacement is the number outside of the parentheses, the base register, which is the first register that you specify, and the product of the scale and the index register. In other words, you take the number, which is the scale, the last number here is the scale, you multiply this to the value of the index register. The product of that will be added to the base register and also the displacement on the outside at the outside of the parentheses, and the summation of all those terms will become the effective address. Okay, is that convoluted, complicated? Not really. Okay, it's just the syntax is okay. The syntax is more convoluted than the concept itself. Okay, if they had chosen a better syntax, it would not be, as difficult to understand. So in this case, in this particular, sorry? Oh, so in this case, in this particular example, we are moving 16 bits. But where are we moving the bit pattern of 25 into? Well, the address is going to be, first of all, we compute the product of whatever the value of EAX is at the time, and we multiply that by 2. Okay? And then we add the product to whatever EBP is, and then we add that sum to -4. In other words, we subtract 4 from the summation of the two of the register and the product of the register and 2. And that becomes our effective address. Okay? Is that okay so far? Okay. And this number here, which is called the scale, can only be 1, 2, or 4. In other words, in the previous slide where we have based index addressing mode, it's basically implying a 1 as our scale. That is all. And as I said, in the cisp architecture, there's a gazillion ways to do something. This is proving that point yet again. And just like with the previous slide, you can also specify no base register. See, in this case, I use only a comma, but without a base register. It works exactly the same way. If you don't specify a base register, the value supplied by the quote-unquote base register becomes just 0. So in this case, we are just computing the product of EAX and 2, and just add that product to L1, and that becomes the effective address. Okay. Are we doing okay so far with this concept? We're doing okay? So I'll just leave it up to you guys to run your own, sample program to just prove me right or prove me wrong. Okay, but it is important to write those simple little programs, because even though each one is so simple, it does not seem to be very useful. It will give you one, a practice of the procedure to assemble, link, and run a program. It will give you a chance to practice your GDB commands, okay? And on top of everything else, it also gives you a chance of actually looking at the program and analyze what each instruction is going to do. It is much better than just reading the notes or just watching the video clip again, because if you actively try to come up with a program, your brain is actually, you're exercising a different part of your brain. It's not just reading something, you're not just absorbing information, you're actually trying to apply what you learned in the class. So that is actually very important. Do we have any questions about these 3 additional addressing modes? No questions? Okay. So what we'll do is we'll go back to a topic or 2 topics that we have skipped at this point. Yep.
Could you also divide?
Hmm?
Could you divide?
Nope, that's it. This is all. This is all that you can do with the addressing modes. Okay. Now we go back to the discussion of CISC versus RISC. Now, let me just do it this way. Let me use a text editor and give you a general equation that makes it very, very easy to understand everything. In other words, I'll give you this. Okay, we have displacement, and then we have the base register, then we have the index register, and then we have the scale. Okay, this is the general format of a memory operand. Okay, because every memory operand is a special case of this, even the direct operand. Right? What is the direct operand with respect to what I have just shown you here? It only has a D. It doesn't have the parentheses, doesn't have any registers, doesn't have any scales. So everything is a special case of this most general form. Okay? So I would say the effective address, which is usually called EA, effective address, of this operand is D plus B plus I times S. That's it. If you don't have a B, that term becomes 0. If you don't have an I, that term becomes 0. If you don't have an S, that term becomes a 1. If you don't have a D, that term becomes 0.
You're not doing anything. And you're not doing anything.
Sorry?
And you're not doing anything.
And you're not doing anything.
I mean, if you don't specify anything on the left-hand side of a move state, you're not doing anything.
Right. This is just an operand. Yep. Question?
Yeah, what was D again?
D is called the displacement. It is the expression that is to the left-hand side of the open parenthesis. You can call it offset or displacement. It's just a number. And that number is added to the base register, and that is added to the product of the index register and the scale. Okay. Are we doing okay so far with this, general equation? Because once you know this one, every single one that we talked about is a special case of this. Yep.
The base value of I and S if they're not listed is 1.
Sorry?
What's the base value of I and S if they're not listed?
0.
Say again, please.
Okay, if you don't use an index or a scale, what are their base values? Like their default values?
The default would be zeros. Right.
Scale would be
For S would be 1. Yes, S is the multiplication factor. But it doesn't make any sense to specify the scale without an index register. You can specify an index register without the scale, but not the other way around. Yep.
Why did they limit it to 1, 2, and 4?
If I remember correctly, 8 may be allowed to, but since I have never really have any applications to use, I haven't really tried the 8. It has to do with, they're only using, 1 or 2 bits or 3, I think it's only 2 bits, to represent the index field. When those 2 bits are 0, 0, it specifies a scale of 1. If it is 0, 1, it specifies a scale of 2. If it is 1, 0, it specifies a scale of 4. And that makes me believe, when you specify 1, 1, it specifies a scale of 8. It has to do with 1, 2, 4, 8 are the popular sizes of integers. They correspond to byte, word, int, and long int in a high-level programming language. And without even explaining any further, you can probably anticipate this general purpose addressing mode is useful for indexing in an array. If you have an array of integers, you can get to any integer of that array in one single operand. You don't have to do any multiplication. You don't have to do any addition because they're all built in to the operand itself. 6 and 7 are not really useful because we typically do not have any integers of that size. You can, but it's just that they're very uncommon. Okay. Any other questions about this general addressing mode? Now, but this is good. This slide is very good because it illustrates that if we have instructions to add and instructions to multiply, there's really no need to have anything that specialized. Because all we can do without something this specialized is we can do all the calculations by additional instructions. I can have add instructions, I can have multiplication instructions to do all the calculations. Instead of rolling everything into a single operand, I can carry out additional instructions to accomplish exactly the same thing. Is everybody convinced that I can get away with not having this kind of addressing mode and just the indirect addressing mode if I have additions and multiplication? I don't even need multiplication. Because if the scales are only 1, 2, 4, and 8, I can just do everything using the addition operation. Adding EAX to EAX is doubling. Adding EAX to EAX again is quadrupling. So I can get away with just addition. So now the question is, why do we have so many addressing modes with the i386? And how does that compare to a RISC processor? That's the question. The question is, which one is faster? Which one is more efficient? Okay? And the answer is not really that clear-cut, okay, because it depends on how you look at it. So why do we want to design RISC processors when we have CISC processors that can do everything in one single instruction, but with a RISC processor, I will have to have additional instructions, okay, because I need to have additional add instructions to do what a single operand can do in a CISC architecture. Well, the first thing you have to remember is, do I need as many instructions, or are there nearly as many opcodes, unique opcodes with a RISC processor? No, because the number of instructions first is reduced. And the second thing is the number of addressing mode is also reduced. So that means, the instruction, you do not need as many bits to specify what you want the processor to do, because you can only select, one from, say, 40 or 60 possible instructions as opposed to hundreds of possible instructions. Is that making any sense so far? Okay. But that also means the processor does not need the silicon or the gates to interpret an instruction, because there are only so many things you can do with a RISC processor as opposed to a CISC processor. So we are talking about a reduced number of silicon or reduced number of transistors in this case. A RISC processor will require much fewer transistors compared to a CISC processor. Hey, well, that makes it cheaper to manufacture. But what about the speed? Because what one CISC instruction can do, you will need like 3 or 4 RISC instructions to accomplish exactly the same thing. Doesn't that make a RISC processor slower? And why not?
Aren't they shorter commands, so you pump them out faster?
That's one, because each command doesn't take as long. But the most important part is, guess what? Inside the Pentium processor, when you have those complicated addressing modes, the instruction itself takes longer, because internally it's still doing everything. It's just that you don't have to see it. So in terms of the number of execution cycles, it will still take a longer time to accomplish the more complicated instructions. Okay. And if you read this whole thing, you will see that the bottleneck these days is power in terms of a data processing center. Now you always want to pack as much processing power as you can into a processing center. Okay, the throughput is how they gauge a data processing center. Before, it is not because of power dissipation, as a bottleneck. Now that is a bottleneck. In other words, how effectively can you cool down a data processing center? Okay, now how does that relate to CISC versus RISC? Now think about all the poor silicon that has to, all the poor transistors inside the processor that has to do stuff, okay, whenever you execute an instruction. With an i386 processor, okay, it is much more complicated because we have all these gazillion ways of doing the same thing. So there are more silicon, there's more transistor that has to be activated in order to do something. But for the most part, many of those transistors are wasted. They have to do something, but what they're doing is not really particularly useful. In other words, you are wasting heat, you're wasting energy, you're wasting power to switch those transistors that normally, if you were using a RISC processor, they do not even need to exist. So that's why when you look at the pure processing power, like MIPS per, when you look at the MIPS, million instruction per second, a CISC processor may, on paper, win over a RISC processor. But that's no longer what we are interested in. We are no longer interested in million of computations per second. We are now interested in number of computations per watt. Okay? Now, can everybody understand the difference? Number of computation per second versus number of computation per watt. Because the limitation now is watt. It is not the second anymore. So that's why the data processing centers now they're shifting from CISC processors back to a RISC architecture. You have to have more RISC processors to have the same type of performance, but the power required for those additional RISC processors is not as much as the CISC processor itself. Okay. So that's kind of interesting. It's an interesting development, because we just cannot get rid of the heat generated in a data processing center today. Yep.
Now, is that a function of we now have higher clock speeds and we also have, smaller chips now? Or is that?
I think it has to do with, before we just do not have the capacity to handle to handle all the results from the computation. So the bottleneck can be storage. Okay, you can process all you want, but you still have to store the data somewhere. And now we may have much more efficient storage, and therefore you can compute more. And the bottleneck is no longer how much you can store or how fast you can store. It is back to how fast you can compute or how much you can compute. Okay, is that making any sense? But it also has to do with clock speed, but clock speed is a function of the size of the transistor. We can only go for a higher clock speed because each transistor is now smaller. It has to do with mostly integration, because if you look at the old 386 motherboard, the components are very spread out. If you look at a 386 motherboard with a thermal imager, you will see that the heat is fairly well spread out. All the components are slightly warm. No one is really, really hot. But when you use a thermal imager to look at a modern motherboard, the heat distribution is no longer even. Okay, the processor and the north bridge, particularly, will run pretty hot, and so will your video processing, your video, the graphics card. But the other components are, they're not really that hot. They're not running that hot. So that means, the concentration is also the why we have the new bottleneck, the new cap, is because how quickly you can extract the heat out of the processors. The latest thing is, they can now stack processors on the silicon die. In the past, we only have like one layer, of transistors. Now they can stack up multiple layers of transistors, and therefore, pack more processing power, onto the same area. Okay.
That's a lot of heat.
But there is a lot of heat to extract. Exactly. So we're getting back to how quickly you can extract the heat out of these processors. And they have, liquid nitrogen and, other types of exotic cooling technology in data centers. And they're still running up against a limit. Yep.
You don't need anything exotic. You can just use a simple fluid cooling system and have your radiator somewhere far away.
You cannot have it too far away, because if it's too far away, then your efficiency also drops.
Yeah, but if you're radiating outside, it doesn't matter how much heat you're putting out. Someone else gets to deal with it.
Oh, that's a classic American.
I think the heat pipes, whatever technology you use to transfer the heat, there's also a limit, of how quickly you can transfer the heat, regardless of, who is getting cooked outside. Now, here's a question for you guys, especially people who like physics and engineering. Would moving the data processing center to outer space help, or would it make it worse? In terms of heat dissipation.
That depends on what your heat dissipation.
Yeah. Let's say the space station is always on the shadow side of the Earth. Okay. Let's just say it never gets exposed to the sun, because that would not be good. Yes. Okay. What do you think? Yep.
There are no particles out there for the heat energy to transfer to, therefore no heat dissipation at all. It would build up into
There's
something
heat
really
dissipation.
hot and
The
melted.
only heat dissipation is by radiation in outer space. Whereas on Earth, you can use air. You can basically have fins and have air as a medium to carry the heat away. So in outer space, it's actually worse off. You're worse off in outer space, unless there's one unless here. Unless you can afford to have a space shuttle to transport dry ice onto the cooling, cooling fins, then you will be better off in outer space. If you can keep a continuous supply of dry ice or some other thing that can evaporate just into outer space.
To the Earth, have just dry ice.
Yeah, but if you run out of dry ice, then your data center is dead in space.
What we should do is build them down at the very, very deepest bowels of the ocean and fluid cool them.
Or just stop using electrons.
Hmm?
So can we stop using electrons?
Well, there are people talking about optical computers as well as quantum computers. So those are very interesting concepts, but they're so far away from production. We don't have to worry about those for some time.
Yeah, but the grad students are having fun with them.
Oh yeah, and IBM too. IBM has a lot of research on those things. Okay, so are we okay with these concepts? Can you relate what we have just talked about to your homework assignment? Do you know how to start with your homework assignment?
No, we know where to start.
Yes.
You don't know how to start, yeah.
Okay, so here let us just take a look at the homework assignment again, and see what we can do to get this started. Now we know that e dx should have a value of this. Okay, at the end. You look at all the instructions that can put something into e dx. I can easily pinpoint which instruction. This one, and this one here. But only one can put something into the most significant 16 bits of EDX. So you have to start with that one, because that one puts the most constraint on everything else.
Which one?
Isn't that the one at the very end, right?
I already said it.
Which one is that?
Only one of these instructions can put something into the most significant 16 bits of EDX. So that is a constraint.
One of those three?
One of those three has to be one of those three, right? I mean, there are only 3 instructions that does anything to EDX. Okay? And then you also have to look at this one here. This is also a big clue, because I am using the indirect addressing mode here and put something back into EAX. In other words, I look at EAX as an address. I go to that location and grab whatever that is back to EAX. So that's also a clue, okay? And then you look at this instruction here. This is another clue. What should be in EAX. Because remember, EAX -1 in this case is an effective address. And I would never go to La La Land and try to grab something out of memory that does not exist. That would not do anything useful. So in order for this to go to a particular part of this memory space that has something that is reasonable, you have to think about, where am I going? So this is like solving a mystery. It's like a Easter egg hunt, but in the form of assembly programs.
I'd rather hunt for eggs. I want chocolate.
So give it a try, and we can talk about it again later on. The first thing you also want to do is to spell out all these locations. Just use a spreadsheet, list out every single byte, so that which label is at which place, in terms of the sequences of bytes. As far as .int L2 is concerned and .int L3 is concerned, you won't know the exact value until runtime. So you just say it takes up 4 bytes, and those 4 bytes point to which other location, because each one is an address.
Wow. That's more complicated than you say. You say it's just those 3. You have to do a lot of things before we.
But why is it any more complicated than anything that we have done so far?
But there's too many clues.
Yep.
Have you actually done this assignment yourself to confirm that it is indeed possible?
Yes, but I was not able to confirm that my solution is a unique solution.
Oh, that's fine. You've already said you'll accept any working solution.
Exactly. So, do we have any questions? I mean, I don't want to give you guys the solution today. I mean, obviously, this one is your homework assignment, and you have a whole week to try to do it. So I want you guys to spend today, in the lab time if you want to, to kind of think about it. You can ask me questions to clarify the concepts, okay? And usually what I will do is I will ask you to write a... Questions? Any questions? No? Okay. Yep.
For the label 1, do we start from label 3 and then find the location of it and come back to number 2 and 1?
The first thing I would do is to just assemble this program, okay? Remove these instructions. Just take this out, comment it out, and comment this out, okay? Just so that the program assembles.
I just want to understand because I don't want to run it and see the values.
You don't want to see the values.
Yeah.
If you don't want to see the values, the way to do it is to use use a spreadsheet or an editor. Just spell it out on a piece of paper. I can do the first part, okay? So basically you just say, okay, this is L1. L1 is a bookmark in your memory space, okay? So L1 is here, and immediately after L1 will be 4 bytes, okay? So you have, these 4 bytes, 1, 2, 3, 4, and these 4 bytes will basically, is L2. But since we don't know what L2 is, we'll just say it is L2. After these, bytes, we have, 2, 3, we have 40, yada, yada, yada. And at some point, we have the label L2, which is another bookmark in memory space. That book immediately after that bookmark would be 4 bytes, which is an address. Every address has 4 bytes, and then that address will be, the value of L3. And then after that, we have, 2 other bytes. Okay, we have 40, we have 23 again, and then we have L3 as another bookmark here. And then that will start with, dot word 23, and 40, and so on. So I would just make a map like this, okay, just so that you know how memory is laid out. Okay. Now the first thing you have to do is to take a look at just these 2 instructions, not the rest of the program. Just take a look at these 2 instructions, and say, what can possibly make this make sense? Okay. If you put, a constant here, it certainly would not make any sense, because you don't know the actual location of the data until the program runs. So if you put any constants like, like 0 or 5 or -5 or whatever here, it certainly will crash. The program will crash and say it's trying to access memory locations out of boundary. Okay? So now you have to think about, okay, of all the things that we have up there, what are addresses? Okay, because you're looking for an address. You want EAX to be a valid address so that you can go to that space and grab 4 bytes and put it into EAX again. So now you have to ask yourself, of all the things that you can use, in place of the question mark, what will specify a valid address? Okay, and that part you already know because you have done the current assignment. Oh, by the way, I have to disclose the current assignment solution, L1 minus 1. Yeah. Okay, so it took 5 seconds to disclose that solution. Yep.
Did you do like that add the hexadecimal and L1 minus 1? It still works out as address.
You need an expression that will resolve to a valid address and put it into EAX.
Yeah, and that's why I did it. It's still valid.
You mean for this one? For this assignment?
For the last assignment.
For the last assignment. Okay. Yep.
Could you explain why if you put the constant, it will not make sense?
Because if you put any constant in place of the question mark, then the second instruction will always go to that location to grab something and put it into EAX. But I already told you the actual location of all this stuff here is determined at runtime. When you actually run the program, the loader will pick a place to put all this stuff here. Okay, and that place can can be different every time you run the program. That place can be different. So that means you cannot use a constant like a literal constant over here. It has to be something that will shift when the loader changes the place, changes the location of where the data section is located. And there are, as far as I can see, there are 3 constructs here that will shift along when the loader loads the data section into different places. We have bookmarks as reference points. Okay, so you have to look for those bookmarks, because remember one advantage of writing programs in assembly is it can be you can refer to labels, and labels can always be resolved later on. You have all these tools to help you resolve the labels. The assembler, the linker, and the loader, they will all help you resolve the labels so that they will always be correct at runtime. Yep.
Can you explain where you do L1 dot int L2? What is that actually doing?
L1.
So for label 1.
Okay, now.
Int L2.
Okay, let's see. The first part is just defining a label. In this case, we know the label is the location of whatever is follows. Okay, so we know that part. The second part is the .int directive, which means we want to allocate 4 bytes, and they have to be initialized to something. The expression of the value they have to initialize to is whatever follows. So whatever follows in this case is L2. In other words, whatever the value of L2 is as a label will be these 4 bytes. Okay?
How does that work with L2 not being? I know that you said it doesn't have have to be referenced yet, but how does that work with it not being used yet? We don't know what's in L2 when we specify.
Because the assembler has what we call fix-up tables. Whenever it encounters a label that has not been defined yet in its own internal data structure, it will remember. Okay, I have just seen L2, and L2 has not been defined yet. So it will make a little note to itself. So later on, when we encounter L2:, it remembers, oh, okay, now we know what L2 is, and by the way, we have these other things to fix up earlier, because they refer to L2. So the assembler can handle that, by itself. You don't have to worry about, forward references because it's not a problem. Yep.
If we put checkpoints between them and run it, so it first encounters L2 without just like reaching you, would it crash at that point? If you just run it step by step and put
no, it's not a problem because
L1 and L2,
it is not a problem because everything is resolved at assemble time already. It doesn't even have to wait until link time because everything. They are resolvable within the same file, and the assembler can resolve everything within the same file. The linker can resolve things between object files, but we only have one object file here, so everything is already fully resolved at assemble time. Yep.
Okay, so we have L1 in L2, so it means that we allocate 4 bytes.
How about this? I give you one more clue. I feel like, what's his name?
Blue?
Is it a blue?
Blue.
Yeah. The blue puppy. Blue's clue.
Despite being blue, she's a girl.
I missed it when Blue could not speak, because later on they have the animated, version of Blue or the real version of Blue, and Blue was actually able to say things, and that was not good. Didn't really work for me. Okay, so let's go ahead and look at one program, and I'll just leave the rest to you guys to think. Okay. This one is not tricky, but it is kind of. I'm trying to come up with a good name of it, but that takes up too much time. So I'll just pick up whatever name. Indirect. Okay. All right. This one is kind of interesting. Okay, so make sure you don't miss anything. Okay.
Right.
Yes, I can type that fast. Okay, here's my program.
Be closer on us.
And it's going to be saved, and I'll upload the program later on. So don't worry about copying the program. Focus on the concept. Okay. Indirect.o, indirect.s, ld, indirect, and we go ahead and run the program. Okay. Take a look at the program. We cannot put a breakpoint on the very first instruction, but that's okay because I don't really care about the value of EAX before the first instruction. So I'll just go ahead and put a breakpoint on the second instruction, which is on line 8, just like that. And before we run the program, I'm interested in what exactly are the 4 bytes at L1. Okay, because it seems kind of circular, right? But it's not. Okay, if you have to think about this from the perspective of the assembler. Okay, the assembler will just process this from top to bottom, and in this case there are no forward references except for _start, which is not important for our discussion. Okay, the first thing it will encounter is L1:, which means I want to define a label called L1, and it is defined to the current location in the data section because we are in the data section at this point. Okay, so that defines what L1 is. L1 is an integer, 32-bit, some kind of value. The next one it will encounter is the .int directive, which tells the assembler, hey, we want to reserve 4 bytes and have those 4 bytes initialized to the value that follows. Well, what is the value that follows? It's not 0, it's not 1, it's not negative 10, it is L1. But L1 is a label that has a value, and that value turns out to be the location of these 4 bytes, right? So as far as the assembler, that's how things are done. And so what we are doing here is we're just moving the address into EAX in this case. This is an immediate operand, and by now you should be able to see it and at least identify which operand is what type. Okay, immediate, register, indirect, and so on and so forth. So all those things, by now you should be able to pinpoint and say, oh, I know what type of operand it is. And everything else are just moving indirect EAX back into EAX. In other words, well, is that going to crash? I mean, can we keep doing this and not have the program to crash? Well, take a look. First thing we want to do is to take a look at one thing. That one thing is a word, but remember a word in GDB is 32 bits. We want to display that thing in hexadecimal, and that thing just turns out to be at label L1. Oh, that's kind of odd. At location 8049098 is the value 08049098. But is that really that odd? Can you do this in C? Yes, we can do it in C.
Yeah, a pointer points to its own memory. To its
Yes.
own address.
Now, but you have to resolve the type because the type would not have matched. So you just need to typecast it, the type itself. And sure, we can do it in assembly. We can do it in C as well.
It's easier to do in assembly.
Because the assembler lets you do anything you want.
Well, C lets us do anything we want. It's just whether or not it accesses from.
For those of you who are familiar with Babylon 5, okay, I refer to science fictions all the time because they are relevant to this class. The assembler are the shadows, and C versus C++, they are the Vorlons. The Vorlons will tell you, you cannot do this, you cannot do that. Everything has to be orderly. There are rules to everything. You cannot do this, you cannot do that, you cannot do this, you cannot do that. If you do, I'll punish you. I'll give you a warning. No, this is not good. I'll give you an error. I will stop compiling altogether and stop everything, right? Whereas the shadow will go like, you want to beat up your neighbor? That's good. That's cool. I'll give you the weapons. Go ahead, beat up your neighbor. That's good for the greater good. It's good for the universe. Okay, so that's the difference between the two. Okay, now C is already considered kind of loose in terms of type checking and stuff like that. There are much more much more strict languages that won't let you do anything. No pointers, no typecasting.
Visual Basic.
Pascal. Okay, so now that we know this, we know the rest of the program is not going to be a problem because I can run the program and I look at EAX, it has this content. I single step, I look at EAX again, and guess what? It's the same. I single step again, I look at EAX again, it's the same. I single step again, and well, you get the idea. It does not change because I'm dereferencing to exactly the same point. The pointers, the value of the pointer is the address of itself. Okay? Yep.
How do you get the number at the first one? This number.
Which number? This number?
Yeah, L1.
L1. Okay, L1 is the label. Remember, L1 is a label, and the label is a bookmark.
What is this number from? How do you get this?
The loader is the last one that touches this number. Okay. In other words, when your program is assembled, it is left as okay. This number will be changed later on, and the object file remembers that. When you link the program, the linker will still remember. Oh, this location will change depending on where I load the data section, and it will make a note. And that's a part of your executable program. The executable file itself contains a table that needs to be fixed up when the loader finishes loading the program. So next, when we actually run the program, which means the operating system, the loader has to load the program into memory, including the data section. Now, once it determines where to load into load into the memory of your computer system, then the loader will say, okay, let me check what else I have to fix up because those instructions depend on this location. And it looks it up and go, okay. And it will say, oh, in this particular program, this is going to float with wherever I load that data section. So the loader will actually go in and fix up all these locations so that they are consistent with the program that you write. So there are a few tools along the way that that will each one will kind of touch it and remember, oh, okay, this location will be determined at runtime, and make a note so that the loader will remember, okay, I have this list of things to fix up once I determine where to load the program. Okay. So are there any questions at this point? Does it help with your homework assignment? I think it helps a little bit. Okay, just the fact that it has the kind of the stuff that you need for your homework assignment. But is the concept okay? Does everybody understand the concept behind this program? Let me quit from the debugger and just take a look at the program using an editor instead. Is the concept okay? Yes?
So kind of the point of this is that a label is an integer. You just can interpret it as
Say that again.
a label is an integer. We can just interpret it as
Exactly. That is exactly right. The assembler is just looking at a label and say, okay, this is a 32-bit or 64-bit pattern. You can look at the 64-bit pattern as a number. You can look at it as an address. You can look at it as 8 bytes if you want to. Okay? So it is only until we run the instruction, then it has quote-unquote a meaning associated with it. Because when you dereference, you are treating that bit pattern as an address. That's the only time when you say, oh, I will look at it as an address. But everywhere else in the program, it's just a bit pattern. Are we doing okay so far with this? Okay, I was about to do one thing, but I cannot remember what I was about to do. Get this back. No, it was related to what we were just talking about, and then I forgot.
Are you going to let us out early?
No. It was important. I remember it was important. Oh my goodness, I'm becoming Walter.
What's related to homework? What's related to homework?
No, I cannot remember.
You had a pop quiz for us.
I cannot remember. Oh, I remember now. Okay. Strawberry milkshake recipe. That's what Walter would say.
Who's Walter?
Walter Bishop from Fringe.
You're on your own there.
I'm always on my own. I always have my own space.
I haven't
Yes.
started watching that one. Is it good? Fringe?
Well, it has its moments. I think I watch it only because of Walter. So
Is
you
that
have.
a movie? Is
It's a
that
TV show.
It's a TV series from Fox. That's the only thing I watch from Fox is Fringe. But wait, everything on Fox is Fringe. Okay, but that works.
Please don't forget what you're doing again.
It's okay, I can
Yeah,
backtrack
tell us
now.
what you're
I push it
doing.
on my stack, so now I can backtrack.
Okay.
Okay. This is what it is. Okay, so basically, what that program is about is a global definition in the C program where you have a void pointer being initialized to itself. Okay, but when you do that, you have to do this because without a typecast, it won't let you get away with it because the address of PTR is void asterisk asterisk. So without the void pointer typecast, the types of these two would not have matched. But essentially, that's what I have done.
Doesn't it have to be cast?
Sorry?
Doesn't it have to be cast with 2 asterisks?
No? No, because it normally would have 2 asterisks, and that's why I need to cast it with 1. Now, we can double check that. I mean, I don't think I have lost it as much as Walter has, but sometimes, I doubt myself. So we'll just do it like this, ptr.c. I only have to compile this program, without even running it. So we'll go ahead and do this. Well, first of all, we'll do it this way first.
Put it in main first.
I don't need a main.
Will it even link without a main?
I don't need to link it.
Just need to compile it.
I just want to compile. I don't need it to link. So it will still work because of a void. Oh, that's because a void pointer can be, anything can be casted to a void pointer, including a pointer to void can be casted to a void pointer automatically. See, I told you C is already kind of loose in terms of type checking, but assembly is even better. Yep.
What happens if you try and cast your mom's phone number to a void pointer?
Black hole. Okay. But it doesn't hurt to cast it, because casting is just redundant, but it won't hurt it. So that's the same thing. But in terms of the meaning, okay, in terms of the meaning of the assembly program that we have just done, you just have to look at it this way. That's what it's doing. Okay? So are we doing okay so far with the concept of L1 : .int L1? Now, I have to use .int instead of .ptr or .pointer because .int is the only thing that I can use that can initialize 4 bytes at once. Okay? Now, before we end this class, let me just show you one last thing to make sure that you guys stay perfectly confused. Okay, so we have .L2. Okay, let's say I want L2 to be the address of 4 bytes that points back to itself. Okay? But let's just say that we don't have .int anymore. I only have .byte. Can I do it with only .byte?
You just do it in reverse order, right?
Yep, you can say .byte, L2, ampersand, 0xFF. That's a bitwise AND. I'm only extracting the least significant byte out of L2. And then we have another .byte to extract the other. So it will be L2, right shift, 8 bits, and then that whole thing ended with FF. And then we have shifting by 16-bit, shifting by 24-bit, and the L1 and the L2 are symmetric definitions. It's just that one is handy because I can spell out all 4 bytes with one single .int. The other one is cumbersome because I am defining each and every single byte individually. But you don't want to take my words. So let's go ahead and invalid sections for operations on L2 and I think that might have to do with the AND operation here. That's okay, we can do a mod. Instead of right shift, I can always divide it. I'm obsessed now. I'm not letting it go.
We appreciate you showing off.
256 won't work.
But this is the kind of stuff that you should have known already. What?
256 won't work.
Oh, that's right.
Divide it by the same thing.
Okay, fine.
What does right shift mean?
Oh, you guys haven't talked about right shift in your C class?
We should have.
Right shift means if you look at the whole thing as a bit pattern, you are just moving the bits. Every bit gets moved over to the right-hand side by 1. Okay, but this one does not have that construct. Oh, what is it? Okay, well, I'll stop here. I won't let my obsession stop you from doing your homework assignment.
Tell the story. You've done it.
Invalid sections are for operations.